Hey there, and welcome to the deep dive. We've got a stack of fascinating notes and articles here today,
We do indeed.
and we're plunging into a topic that, well, it sounds subtle, but it has some pretty big implications. Something called gravitational redshift.
hmm And the amazing data coming from the European Space Agency's Gaia mission. It's really giving astronomers completely new ways to measure and understand this effect.
Yeah, it's incredible. So maybe start with the basics, like the siren analogy you mentioned earlier.
Right, okay. You know how the pitch of a siren changes as it zooms past you? That's the Doppler effect.
Yeah.
Light does something similar.
Okay.
A star's motion towards or away from us makes its light shift wavelengths. That's the Doppler shift. And it tells us its radial velocity, how fast it's moving towards or away from us.
Simple enough.
But, and this is the key point from your sources, there are other really tiny effects that can also subtly shift the wavelength of starlight.
Ah, okay.
And for the kind of high-precision astronomy you need to, say, find exoplanets or map out how the galaxy moves, these small shifts, they really matter.
And today, we're zooming in on one specific effect, gravitational redshift. You said it's caused by the star's own gravity.
Exactly. The star's gravity puts a little pull on the light as it tries to escape.
Okay.
Traditionally, we measure radial velocity using spectroscopy,
Mm-hmm.
you know, splitting the star's light into a rainbow and looking at shifts in the dark spectral lines.
The standard method.
Right. But Gaia's incredibly precise astrometry. Its geometric measurements of where stars are and how they move across the sky lets us figure out radial velocities in a completely different way, geometrically.
Ah, so two independent ways to get velocity?
Precisely. And here's the kicker. The difference between the velocity you get from the spectrum and the velocity you get from Gaia's geometry, that difference can reveal these other subtle shifts, the ones that aren't just about the star moving through space.
It's like gravitational redshift.
Gravitational redshift is a big one, yeah.
So our deep dive today is all about unpacking this. What gravitational redshift is, why it's suddenly such a big deal with Gaia, and how these recent studies using white dwarfs, stars and clusters, even wide binary systems are giving us some really compelling insights. It's all here in the material.
Sounds like a plan. Let's start with a core idea then. What is gravitational redshift, fundamentally?
Yeah, break it down for us.
Okay. Your sources explain it using Einstein's general relativity. Basically, gravity actually affects time itself. It slows it down just a tiny bit.
Right. Gravity warps space-time.
Exactly. So, for a photon of light trying to climb out of a star's gravitational field, it's like time is running slightly slower down where it started compared to further out. This causes its wavelength to get stretched out a little.
Stretched, meaning shifted towards the red end of the spectrum.
Precisely. Shifted towards red. That's gravitational redshift.
So gravity literally stretches the light waves. The sources also mention framing it as a spectroscopic velocity offset. Why that terminology?
Well, think about it. Velocity towards or away from us shifts the light's wavelength. That's the Doppler shift. Gravity also shifts the wavelength.
Okay.
So when you look at a star's spectrum, the total shift you see in the lines is partly due to its real motion and partly due to this gravitational effect. And that gravitational part looks exactly like the star has a tiny extra velocity pushing it away from us.
Ah, I see. So it mimics a Doppler shift in the spectrum, even though the star isn't actually moving faster away.
You got it. It manifests as an apparent velocity offset.
Got it. So how big are we talking? Is this a huge effect or tiny?
Well, it really depends on the strength of the gravity. For light leaving our own sun, the redshift is equivalent to a Doppler shift of about 636 meters per second.
Meters per second. Okay.
And for light escaping Earth, it's minuscule, like 0.2 meters per second. Barely anything.
Right. So for most stars like the sun, 600-ish meters per second, that doesn't sound like a game changer. Can we even measure that easily?
You're right. For most sun-like stars, it is relatively small, maybe a few hundred meters per second. And importantly, it's often comparable in size to other subtle shifts, things happening in the star's atmosphere, like convective blue shift.
Convective blue shift? What's that?
That's caused by the churning motion of gas on the star's surface. Hot gas rising up gives off slightly blue-shifted light.
Mm-hmm.
So isolating just the gravitational redshift part using only spectroscopy is tricky for normal stars.
Okay, so it gets mixed in with other small effects, but the material you shared really emphasizes white dwarfs. You said they're completely different.
Oh yeah, they're the true gravitational redshift champions. Absolute superstars for this.
Why? What makes them so special?
It's their structure. They're incredibly dense. You have maybe the mass of the sun packed into a ball roughly the size of the Earth.
Whoa.
So tiny radius, huge mass means extremely high surface gravity. And that means the gravitational redshift for light escaping a white dwarf isn't just meters per second, it's tens of kilometers per second.
Tens of kilometers per second compared to hundreds of meters for the sun.
No.
That's enormous.
It is a factor of like 100 bigger.
Mm.
And because the effect is so dominant, so huge, your notes highlight a really crucial point.
Which is?
For a white dwarf, that difference, we talked about the difference between its spectroscopic velocity, which has that big gravitational redshift baked in, and its astrometric velocity from Gaia, which is just its pure motion, that difference becomes a direct proxy for its mass.
Wait, so you can essentially weigh a white dwarf just by measuring how much its gravity stretches its escaping light? That's amazing.
It really is. And astronomers have known this in principle for a while. They've made direct measurements of this effect for white dwarfs going back decades, actually.
Oh, really?
Yeah, your sources mention classic studies from the 60s and more recent ones, too. They've even measured it for neutron stars, where gravity is even more insane.
Wow. And wasn't there a specific famous example mentioned? Sirius B?
Yes, exactly. Sirius B. It's the faint white dwarf companion to the really bright star Sirius A. Studies of Sirius B have shown pretty convincingly that the mass you calculate based purely on its gravitational redshift. It matches up beautifully with the mass you get totally independently by watching how it orbits Sirius A.
So the orbital mechanics and the light stretching effect give the same answer for its mass.
Precisely. It's a really powerful confirmation of the whole idea.
Okay, so white dwarfs are the perfect test subjects. How has Gaia data specifically pushed this field forward? What new things are we learning?
Well, the studies you brought highlight a couple of key ways Gaia is making a difference. One study, Pasquini and colleagues in 2019, they looked at a small group, just 6 white dwarfs, but they were all in the Hyades star cluster.
Okay, a cluster gives you stars with similar properties. What did they compare?
They used high-resolution spectra from ground-based telescopes that gives the spectroscopic velocity and combined it with Gaia DR2 astrometry for the pure motion component.
And when they calculated the mass from that gravitational redshift difference?
Here's where it got interesting. They found that the masses they derived, just using this redshift method, were consistently a little bit smaller than the mass estimates they got using other, more established methods.
Smaller. By how much?
By about 0.02 to 0.05 times the mass of the Sun. It sounds small, but your notes call this a potentially significant finding. It suggests that maybe, just maybe, our standard models for white dwarf structure or evolution might need some fine-tuning.
A systematic discrepancy. That's definitely intriguing. What about the other study mentioned, Chandra et al.?
Right, that one took a different tack. Chandra and collaborators in 2020 used a much, much larger sample, like 3,000 white dwarfs.
Wow, okay. Where did they get the data?
They combined data from the Sloan Digital Sky Survey, which has tons of spectra, with Gaia DR2, which provides those crucial precise distances, or parallaxes.
And the distances let them calculate radii.
Exactly. So they had spectroscopic velocities, radii from Gaia parallaxes, and they could estimate surface gravities.
So how did they isolate the gravitational redshift with such a huge, diverse sample? Weren't the individual motions all over the place?
They were, but they used a clever statistical trick. They grouped the white dwarfs based on their measured radii and surface gravities. Then, for each group, they averaged the spectroscopic velocities.
Average them. Why?
Because a random Doppler shifts from the star's individual motions, some moving towards us, some away, should average out to 0 if you have enough stars.
Ah, canceling out the noise.
Exactly. What's left, the average velocity offset for that group, should be dominated by the underlying gravitational redshift common to white dwarfs with those particular properties.
That's smart. So they could effectively measure the relationship between mass and radius just using this statistical redshift signal.
Yep, it allowed them to empirically map out the white dwarf mass-radius relation using gravitational redshift as the key measurement.
And what did they find? Did it confirm the discrepancy the other team saw?
Interestingly, no. Their results, based on this large statistical sample, were actually quite consistent with the leading theoretical models for white dwarfs, specifically mentioning models from Fontaine and colleagues back in 2001.
So one study hints at a tweak needed, another validates the existing picture using a new technique. Science in action.
Pretty much. It shows how different approaches, sample sizes, and maybe even the specific stars looked at can sometimes give different perspectives. Needs more investigation, clearly.
Okay, so before Gaia, it sounds like measuring this effect reliably was pretty much limited to the sun, where it's tiny, and white dwarfs, where it's huge.
Largely, yes.
Yeah.
The precision just wasn't quite there for most other stars. But Gaia's changed that, opening the door to studying this in other stellar populations, like star clusters.
Right, you mentioned clusters earlier. Why are they so useful here?
Well, as your notes point out, the stars in an open cluster, they all form together, roughly same age, same composition, and crucially, they move through space as a group. They share a common overall motion.
Like a swarm of bees moving together.
Kind of, yeah. And Gaia measures that common motion incredibly well. That gives you a baseline.
Okay.
So by comparing the spectroscopic radial velocity of an individual star within the cluster to the cluster's average motion measured by Gaia, you can look for tiny differences.
Differences that aren't just random scatter.
Right. Differences that might be caused by things like gravitational redshift or that convective blue shift we mentioned, even for normal dwarf stars or giant stars, where these effects are much smaller than in white dwarfs.
So clusters let you study these subtle effects statistically across many stars.
Exactly. It's a way to test fundamental physics, like the equivalence principle, and also to refine our models of how stars work internally.
Makes sense. Let's dive into some of those cluster studies mentioned in the material.
Okay, one early-ish one, Leo and collaborators in 2019. They looked at the Hyades cluster again, using a mix of older Hipparcos data and the newer Gaia DR1 astrometry, plus ground-based spectra. They studied dozens of normal main-sequence stars and a couple of giant stars.
And what did comparing the spectroscopic and astrometric velocities show them?
Well, first, the overall pattern of differences matched the known rotation of the Hyades cluster itself, which was a nice sanity check.
Yeah.
But here's the cool part. They found that the two giant stars in their sample showed a distinct blue shift compared to the average dwarf star.
A blue shift, not a red shift.
Blue shift, yeah. By about 626 meters per second, plus or minus some uncertainty. And this actually matched theoretical predictions really well.
Why would giants be blue shifted?
It comes back to that convection. Giant stars have much more vigorous convection on their surfaces than dwarf stars like the Sun. This stronger churning leads to a stronger convective blue shift effect, which in their case overwhelmed the gravitational redshift.
Ah, so they were seeing the interplay of both gravity and convection.
Precisely. It showed they could start disentangling these different subtle effects.
Okay, what about other cluster studies? There was one with a huge sample mentioned.
Right. Day et al., also 2019. They used a massive sample from Gaia DR2, over 700,000 stars, F, G, K types like our Sun, plus red giants, all relatively nearby.
And they looked at the total shift.
Yeah, they focused on measuring the total intrinsic redshift, which is the sum of the gravitational redshift plus the convective blue shift for each star type.
And what did that total reveal?
For the normal FGK stars, they found the total intrinsic shift was actually quite small, significantly smaller than what you'd expect just from gravity alone. Meaning the convective blue shift must be pretty substantial in these stars, largely canceling out the gravitational redshift effect. There was balance.
Interesting. And for the red giants?
For the red giants, they found the total intrinsic shift was negative and overall blue shift.
Which fits with the Leon study finding blue shifted giants.
Exactly. It confirmed that for giants, the stronger convective blue shift dominates over their slightly weaker gravitational redshift because they're puffier.
Yeah.
It all lined up with theoretical expectations.
So Gaia's precision in these big cluster samples is really letting us test and refine our understanding of stellar atmospheres and gravity.
Yes, statistically separating these effects across large populations. And there's one more recent study, Gutierrez et al., 2022. They used Gaia DR2 data, again, focusing specifically on stars in tens of thousands of open clusters. They picked a really high-quality subsample.
Okay.
Nearly 4,000 stars across almost 30 well-studied clusters like the Pleiades, Praecipi, clusters like that.
And what was their approach?
They took theoretical estimates for how strong the convective blue shift should be for each star based on its properties. Then they compared those theoretical predictions with the actual observed velocity differences, the combined effect of gravity and convection measured by comparing spectroscopy and Gaia astrometry.
So comparing theory directly to observation for this combined effect, how well did it match?
According to your source, the correlation was incredibly strong, like 0.977 correlation coefficient, almost perfect agreement within the uncertainties. Your notes actually call this one of the more extensive validations of a fundamental prediction of gravity theories. Using stars. It's like using whole clusters as giant physics labs.
That's really impressive, using these collections of stars. Okay, so speaking of using common motion as a lab, Your sources mention another type of system, wide binary stars.
That's right. Similar idea to clusters, actually.
How so?
The two stars in a wide binary pair, stars born together but now orbiting each other at a large distance, they share common overall motion through space, just like cluster members.
Okay, makes sense.
So by looking at the difference in the measured radial velocities between the two stars, you can again try to cancel out that shared bulk motion. What's left should be the relative differences caused by effects intrinsic to each star.
Like their individual gravitational redshifts and convective blue shifts.
Exactly. It's mainly the combination of those two effects you're sensitive to. Your sources note that this is mostly feasible statistically right now, looking at averages over many pairs.
And I bet Gaia has been revolutionary for finding these pairs.
Oh, absolutely. Before Gaia, finding large, clean samples of truly wide, physically bound pairs was tough. But Gaia's ability to measure precise motions and distances for billions of stars has led to huge catalogs. We've gone from maybe hundreds or thousands to like tens of thousands, even close to 100,000 likely wide binaries identified in recent Gaia data releases.
That's a massive increase in sample size for these kinds of studies.
Huge. It unlocks the statistical power needed.
So how have astronomers put these big, wide binary catalogs to use for studying redshift?
Well, one study highlighted is Muscella and colleagues in 2022. They used over 1,600 wide pairs from Gaia DR2, focusing on pairs where they also had estimates for the star's temperatures, luminosities, radii, things that let them estimate surface gravity and convective effects.
Okay, so they had predictions for the effects. Did they see them in the velocity differences?
They did. They found a clear correlation between the observed differences in the Gaia radial velocities for the two stars in a pair and the predicted differences based on their individual properties, combining the expected gravitational redshift and convective blue shift for each star.
So the measured differences matched what theory predicted.
Statistically, yes. Your notes emphasize they could rule out a null result, meaning no correlation, with very high confidence, like 5 sigma. So they definitely detected the signature of these combined subtle effects within the wide binary population.
Very cool. Detecting gravity and convection statistically just by comparing pairs of stars moving together.
And then there's another more recent study by Kareem El-Bandri in 2022, this one using Gaia DR3 data. He focused on a specific type of pair, about 500 wide binaries where one star was like our sun, a main sequence star, and the other was a red giant or a red clump star.
Okay, a specific pairing. What was the key finding there?
He found that on average, the apparent radial velocity of the giant star was consistently lower than the apparent radial velocity of its main sequence companion.
Lower by how much?
By almost half a kilometer per second on average, 0.49 kilometers plus or minus a small uncertainty.
And what's the explanation for that systematic difference between the giant and the dwarf?
According to your source, it's primarily driven by the difference in gravitational redshift between the two stars.
Oh, so.
The red giant is much larger, more puffed up than the main sequence star, so its surface gravity is weaker.
Right.
Weaker gravity means less gravitational redshift for the light escaping the giant. The main sequence star is denser, has stronger gravity, so its light gets redshifted more.
Ah, so the giant's light is less redshifted, making it appear to have a slightly lower velocity in the spectrum compared to its companion, even though they're traveling together.
Exactly. And this measured average difference was in pretty reasonable agreement with theoretical predictions that combine both the expected gravitational redshift difference and the expected convective shift differences between these types of stars.
So multiple lines of evidence clusters, wide binaries, pointing towards our ability to measure and model these subtle effects thanks to Gaia.
It seems so. The precision is really key.
Okay, so let's connect all this to the bigger picture. The sources you provided wrap up with a couple of broader implications from these kinds of precise measurements. What are they?
Right. One really fascinating connection, which Avi Loeb highlighted in a 2022 paper referenced here, links back to those wide binaries and the whole topic of modified gravity theories.
Modified gravity, like theories that suggest gravity works differently than Einstein predicted on large scales?
Exactly. Loeb pointed out that the difference in gravitational redshift we just discussed, the one between dwarf stars and giant stars in wide binary systems, especially ones that are quite far apart, is actually pretty significant.
Okay. Why is that important in the context of modified gravity?
Well, Loeb proposed that this standard gravitational redshift effect was likely misinterpreted in some earlier studies. Your notes mention one by Hernandez and collaborators, also referenced in a previous essay we discussed, #37, which used earlier Gaia data, EDR3.
What did those earlier studies suggest?
They had looked at the orbital dynamics of wide binaries and found some subtle anomalies, hints that maybe the stars weren't moving quite as expected under standard Newtonian or Einsteinian gravity at those large separations. They floated it as possible evidence for needing modified gravity.
But Loeb is suggesting it might just be standard gravitational redshift fooling us.
That's the suggestion in the source, yes. That the apparent velocity differences caused by gravitational redshift, which is a totally standard effect in general relativity, might actually be large enough to explain the subtle velocity patterns observed in those wide binaries, without needing to invoke any new physics or modifications to gravity.
Wow, okay. So properly accounting for these subtle effects is crucial before we jump to conclusions about fundamental physics needing an overhaul.
It certainly argues for careful consideration of all known effects.
What's the second big implication mentioned? It connects to the Milky Way itself.
Yes, this one ties gravitational redshift to the overall dynamics of our entire galaxy. Studies using Gaia data, like Gaia EDR3, have given us a much clearer picture of how the Milky Way rotates.
Right, the rotation curve.
Exactly. It seems the Milky Way has a mostly flat rotation curve out to large distances. Stars, including our Sun, orbit at a roughly constant speed around 230 kilometers per second locally, although it might decline slightly further out.
Okay, and that rotation implies a certain overall gravitational field for the galaxy.
Correct. And Loeb, in that same 2022 paper, pointed out that the galaxy's overall gravitational potential itself has a subtle effect on the light traveling from distant stars to us related to gravitational redshift.
How does the galaxy's gravity affect the light like that?
It causes an apparent shift in their measured radial velocities, depending on where they are relative to us and the galactic center.
Apparent, meaning not their true motion.
Right. It leads to this effect described as apparent radial migration. Stars that are physically located closer to the galactic center than the Sun tend to appear as if they are slightly receding away from us when we measure the radial velocity via spectroscopy.
Even if they aren't actually moving away from us.
Correct. And conversely, stars that are physically further out from the center than the Sun tend to appear as if they're slightly approaching us.
Why does that happen?
It's a consequence of the light traveling through the galaxy's changing gravitational potential on its way here. The slight difference in the gravitational potential between the star's location and our location imprints a tiny systematic wavelength shift, a gravitational redshift or blue shift, due to the galaxy itself that mimics a radial velocity.
So the galaxy's own gravity creates a subtle systematic bias in our radial velocity measurements that depends on galactic location.
That's the idea. It's another layer of complexity, another subtle effect that high-precision data like Gaia is forcing astronomers to confront and account for as they try to build an accurate map of the true 3D motions and structure of our galaxy.
This has been, well, a really deep dive into what initially seemed like maybe a tiny niche effect, but it clearly has some major implications.
It really does.
We've explored how astronomers are using Gaia's incredible precision, often pairing it with traditional spectroscopy, to finally measure these fundamental wavelength shifts caused by gravity itself.
And we've seen how it's leading to tangible results. Better mass measurements for dead stars like white dwarfs, ways to test our models of how stars work, providing these quite compelling validations of gravity theories using star clusters.
And helping disentangle those complex combined effects of gravity and convection in binary stars.
Yeah, it's pushing the field forward on multiple fronts.
What really stands out to me is how looking at these subtle differences, the tiny mismatch between geometric measurements from Gaia and spectroscopic shifts, can unlock such fundamental properties of stars, and how it even ripples outwards to affect our understanding of the entire galaxy's dynamics.
It underscores the power of precision measurement in astronomy. When you can measure things just that little bit better, sometimes whole new avenues of investigation open up.
It's really amazing, isn't it, when you think about it? Measuring a seemingly tiny stretch in starlight, maybe just a few hundred meters per second for a normal star, forces us to think about the fundamental nature of gravity and time itself. And now we see it can even subtly warp our picture of how stars are moving way across the Milky Way. Definitely something for you, our listeners, to ponder next time you look up at the night sky.